Hello everyone, this is Saurabh from Edureka, and in today's video we are going to discuss what's new in Hadoop 3. We'll see what all things we can expect from it as it is still there in alpha phase. So let's move forward and have a look at the agenda for today. First we'll see how Erasure coding will reduce the storage overhead in HDFS as compared to replication. Then we'll see the changes with Yarn Timeline Service version 2, and we'll also see the changes in shell script rewrite in Hadoop 3. After that, we'll understand the shaded client jars and how are they useful. Then we'll focus on how Hadoop 3 is incorporating opportunistic containers with guaranteed containers. After that, we'll see how native Java implementation is going to optimize the performance. Next up, we'll see the high availability architecture with two passive name nodes. Then we'll talk about few default ports that have been changed in Hadoop 3. And finally, we'll focus on Intra-DataNode Balancer. Fine guys, we'll move forward and see what all changes we can expect in Hadoop 3. So all Hadoop jars are now compiled targeting a runtime version of Java 8. That means if you are planning to switch to Hadoop 3, you need to make sure that you have Java 8 or versions of Java released after 8. Next up, we'll see how Erasure coding will reduce storage overhead in HDFS. So in Hadoop 3, they have introduced Erasure coding to reduce the storage overhead. Now let me explain how. Earlier, before Hadoop 3, in Hadoop 2, there were replicas made for the data blocks that were stored in the data nodes. Now, by default, the replication factor is 3. So we'll take that same example. So if you have two data blocks, that means our overhead is around 200%. So now let's move forward and see how it is actually getting reduced with the help of Erasure coding. So basically, Erasure coding has reduced the storage overhead by almost 50%. Let me tell you how. If you can remember in the previous version of Hadoop, that is Hadoop 2.x, there was a replication of the data blocks, or you can say copies of data blocks kept across the various data nodes. Now by default, the replication factor was 3. Because of that, every data block that is there in the data node is present in two other data nodes as well. Now because of that, if you can see that there is 200% overhead. And at the same time, there are certain cold data sets as well that we rarely use. Because of this, we are actually wasting a lot of resources by creating replicas for those cold data sets. Now let us see how Erasure coding actually solves that problem. Now in Erasure coding, what happens, there is RAID. RAID is nothing but redundant array of independent, or you can say inexpensive disks. Now whatever the data that you have is segmented into small blocks, and these blocks are stored in various disks, as you can notice in the diagram that I'm highlighting with my cursor right now. Now for each strip of original data cells, a certain number of parity cells are calculated and stored, the process of which is called encoding. So if I take the example, suppose block A1 and block A2. So these are two data blocks, and we generate a parity block out of these two data blocks. This is block AP. Now why we do that? Let's focus on this particular diagram and understand that. So over here, if any failure happens, if you can see there's a question mark, so I don't have my block A1 anymore. Now what I can do, I can actually use this parity bit along with this block A2, and I can recover this block A1. So this is how I can perform error recovery using Erasure coding. Now let's move forward and see what benefits we get with this. Now in order to explain you the benefit, I'll take an example. Suppose if I have 3x replicated file with 6 blocks, that will consume around 6 into 3 equals to 18 blocks of disk space. But with irrational coding, 6 data and 3 parity blocks will only consume 9 blocks of disk space, and it will be as reliable as replication. And at the same time, if you can notice that there is only 50% overhead as one parity block stored for 2 data block. Now let me tell you one very important thing here guys. So what you can do is, suppose if you want to have 5 replications, so you can keep 3 replications and you can generate 2 parity blocks. So in that way, you can actually reduce the overhead. So this is how Erasure coding has solved the storage overhead problem in Hadoop 3. Fine guys, so in order to perform this Erasure encoding, we need to make sure that there are certain changes in the architecture of Hadoop. So let us see what those changes are in Hadoop 3. So the first thing is Namenode extension. So we have seen earlier as well that we have stripped HDFS files, right? So whatever files that we have are broken down into small blocks, and these blocks can actually form a block group in which there will be certain number of internal blocks. Now because of these many blocks, the metadata that Namenode has to contain will be huge, and it will require a huge amount of disk space. So in order to reduce the Namenode memory consumption from these additional blocks, a new hierarchical block naming protocol was introduced. The ID of a block group can be inferred from the ID of its any internal blocks. So basically the block group ID, or you can say the block pool ID, will be there in the name node, and using that you can actually figure out which data block is stored in which particular block group. And this allows management at the level of block group rather than the blocks. And the next change is client extension. So basically the client read and write paths are enhanced to work on multiple internal blocks in a block group in parallel. So as we have seen that a block group contains multiple blocks, so we can actually perform the read and write operation on those multiple internal blocks at the same time. Fine guys, so we'll move forward and see some other changes in the architecture. So the third change was a data node extensions. So the data node runs an additional Erasure coding worker called as EC worker task for background recovery of failed Erasure coded blocks. The failed Erasure coded blocks are detected by Namenodes, which then chooses a data node to do the recovery work. So in order to do that, there are three key tasks that it has to perform. So the first is it actually has to read the data from the source nodes. Then it has to decode the data and generate the output data. So what does that mean? Whatever the parity block that we have generated and the other data block, it will use both of them and then it will generate the data block that we have lost. Then what will happen? It will transfer the generated data block to the target nodes. Now the fourth point is Erasure coding policy. Now basically it determines that what sort of Erasure coding schema will be there and on what basis you'll divide or split your data blocks. It can be on the basis of bits or it can be on the basis of size. So on what basis you'll do that. So this is basically what Erasure coding policy is. Now we'll move forward and understand the Yarn timeline service version 2. So as we all know that in Hadoop 2, Yarn version 1 was present. But in Hadoop 3, Yarn timeline service version 2 was introduced. It addresses two major challenges. First is improving scalability and reliability of timeline service. And the other is enhancing usability by introducing flows and aggregation. This Yarn timeline service version 2 alpha 1 is provided so that users and developers can test it and provide feedback and suggestions for making it a ready replacement for timeline service version 1.x. It should be used only in a test capacity. Most importantly, security is not enabled. So do not set up or use timeline service version 2 unless security is implemented, if security is a critical requirement. Yarn version 1 is limited to a single instance of a writer/reader and storage and does not scale well beyond small clusters. Yarn timeline version 2 uses a more scalable distributed writer architecture and a scalable backend storage. Yarn timeline service version 2 separates the collection of data from serving of data. Basically, it separates writes and reads. It uses distributed collectors, essentially one collector for each Yarn application. The readers are separate instances that are dedicated to serving queries via REST API. Yarn timeline service version 2 chooses Apache HBase as a primary backing storage, as Apache HBase scales well to a large size while maintaining good response times for reads and writes. In many cases, users are interested in information at the level of flows or logical groups of Yarn applications. It is much more common to launch a set of series of Yarn applications to complete a logical application. So Yarn timeline service version 2 supports the notion of flows explicitly. In addition, it supports aggregating matrix at the flow level. Also, information such as configuration and matrix is treated and supported as first-class citizens. The diagram illustrates the relationship between different Yarn entities modeling flows. So as you can notice here that we have flows here, which is subdivided into flow run 1 and flow run 2. Then again it is subdivided on the basis of applications. We have application 1, 2, 3 and 4. Then again it is divided on the basis of attempts. And finally we have containers, and we know that it is used to just provide the execution environment. Yarn timeline service version 2 uses a set of collectors to write data to the backend storage. The collectors are distributed and co-located with the application masters to which they are dedicated. All data that belong to that application are sent to the application level timeline collectors. For a given application, the application master can write data for the application to the co-located timeline collectors. In addition, node managers of the other nodes that are running the containers for the application also write data to the timeline collector on the node that is running the application master. The resource manager also maintains its own timeline collector. It emits only yarn generic lifecycle events to keep its volume of writes reasonable. The timeline readers are separate daemons, separate from the timeline collectors, and they're dedicated to serving queries via REST API. Fine guys, so we'll move forward and we'll focus on the shell script rewrite part in Hadoop 3. So the Hadoop shell scripts have been rewritten to fix many long-standing bugs and include some new features as well. But we need to keep an eye towards compatibility. Some changes may break the existing installations. Now let's move forward and see shaded client jars. So Hadoop client, which was there in Hadoop 2.x, pulls the Hadoop transitive dependencies in the Hadoop application paths. So this creates problem if the version of the dependencies conflict with the version used by the application. So basically what happens in Hadoop 2.x, whatever dependencies for your applications are there, for that you need to import certain jar files. So sometimes what happens, the version of these dependencies conflict with the version used by the application. So in order to solve that, Hadoop 3 adds new Hadoop client API and Hadoop client runtime artifacts that combines Hadoop dependencies into a single jar. So whatever dependencies are there for your application will be combined into a single jar. Now this Hadoop client is the compile scope and runtime is the runtime scope. That contains third-party dependencies from the Hadoop client. So whatever dependencies are there, it is converted into a single jar and then it is checked. So instead of checking it again and again, we can combine all the dependencies into a single jar file and then we can compile it and then we can check it. So basically this avoids leaking Hadoop dependencies into application path. I'll give you an example for that. HBase can use to talk with a Hadoop cluster without seeing any of the implementation dependencies. So we'll move forward and understand opportunistic container. So basically in Hadoop 3, there is a new type of a container that has been introduced, which is called opportunistic containers. So earlier we had only guaranteed containers, but now we have opportunistic containers. Let me explain you what it is. So these opportunistic containers can be dispatched for execution at a node manager even if there are no resources available at the moment of scheduling. Now at the moment of scheduling, if you can remember, in the guaranteed containers, if there are no resources, it won't provide the execution environment. But that doesn't happen in the opportunistic containers. So what happens if there are no resources in opportunistic containers? In that case, these containers will be queued at the node manager, waiting for resources to be available for it to start. And let me tell you guys, opportunistic containers are of a low priority than the default guaranteed containers and are therefore preempted if needed to make room for guaranteed containers. This improves your cluster utilization. Opportunistic containers are by default allocated by the central resource manager, but support has also been added to allow opportunistic containers to be allocated by a distributed scheduler, which is implemented as an application master resource manager protocol. So basically in the guaranteed containers that were there in Hadoop 2, it has to wait for the node manager to provide it with the resources and then only it will process the requests that are there. But in opportunistic containers, it will be queued at the node manager waiting for resources to be available for it to start. That's the only difference here. And we know what advantage it provides. Basically, it improves your cluster utilization. So Mapreduce has added support for native implementation of the map output collector for shuffle intensive jobs. This can lead to a performance improvement of 30% or more. It adds a native implementation of the map output collector. The native library will build automatically with pnative. For shuffle intensive jobs, this may provide speed ups of 30% or more. So we know what are shuffle intensive jobs. And let me tell you guys, this is only there till the mapper phase. For reduce phase, it is not present. So they're recently working on the native optimization for the map task based on JNI. The basic idea is that add a native map output collector to handle key value pairs emitted by mapper. Therefore, sort spill can all be done in native code. Their preliminary test on Xeon E5410 and JDK6U24 showed very promising results. And let me tell you guys, sort is about 3 to 10 times as fast as Java. And this led to a total speed of speed up of about 2x to 3x for the whole map task. And keep this thing in mind that the merge code is still in development phase. All right. So let's move forward and see how high availability has been achieved in Hadoop 3. Hadoop 3 actually supports more than 2 name nodes. And in the previous version of Hadoop, we know that it supported only 2 name nodes. One was active and another one was passive. So this was the case in Hadoop 2. We have one active node, one passive node, and we have journal nodes. So these journal nodes are used in order to synchronize both of these nodes. There'll be only one active name node which will be monitoring your data nodes, and there'll be one passive node which will actually contain the metadata that is stored in the active name node, so that if it fails, it can actually take its place. So that passive can become the active name node. And as I've told you earlier as well, these journal nodes are used in order to synchronize both of these. And what sort of synchronization? Basically, whatever metadata is there in the active name node will be there in the passive name node. And apart from that, it also makes sure that there is only one active node present at one instance. So this was Hadoop 2. Now let us see Hadoop 3. What are the changes? So in Hadoop 3, we have actually 3 name nodes. That is one active name node and we have 2 passive name nodes. And apart from that, we have 5 journal nodes. And I've told you earlier as well, these are used in order to synchronize these multiple name nodes. So this architecture actually provides high availability because even if 2 of your name nodes fail, we have one more name node that can take its place. Next up, we'll see what all ports have been changed in Hadoop 3. So previously, the default ports of multiple Hadoop services were actually there in the Linux ephemeral ports range between 32768 to 61000. And we know that ephemeral range is nothing but a few ports that are required by Linux services. So what happened at startup, services would sometimes fail due to conflict with another applications. So in order to solve this, conflicting ports have been moved out of the ephemeral range. Now let's see what all ports have been changed. So for name node ports that were there earlier in 50470 has now become 9871. Similarly, 50070 has now become 9870, and the rest of it you can see it on your screen right now. So we'll move forward and understand object storage file system connectors. So over here they have integrated Hadoop 3 with Microsoft Azure Data Lake and Aliyun object storage system file system connectors. So Hadoop 3 now supports integration with Microsoft Azure Data Lake and Aliyun object storage system as alternative Hadoop compatible file systems. So that's all, guys. This is the maximum that I can tell you about it right now. It is still in alpha phase, as I'm telling you again and again. Fine, guys. So let's move forward and see one more change. So it is about having Intra-DataNode Balancer, which was not there earlier. So what used to happen, let me show it to you with a diagram. So this was a condition in Hadoop 2. So what happened in Hadoop 2, a single data node manages multiple disks. As we have seen earlier as well, that there are multiple disks in the data nodes, and these disks contains small data blocks. So during normal write operation, disk will be filled up evenly. So whenever you're writing some data in the data nodes, it will be filled up evenly in different disks that are present in one data node. However, adding or replacing disk can lead to significant skew within a data node. But when you are actually adding or replacing disk, that can lead to significant skew within a data node. That means some data block might contain more data, whereas other data blocks might have less data. So because of that, when you're accessing the data, some disks will take more time, whereas other disks will take less time. And this situation is not handled by the existing HDFS balancer, which concerns itself with the inter, not intra-data node skew, which means that it mostly focuses on the data blocks to be distributed evenly among different data nodes, but not between the different disks within the same data node. So this situation is handled by the new intra-data node balancing functionality, which is invoked via the HDFS disk balancer CLI. And it is nothing but used to make sure that all of your data is evenly distributed among these disks which are present inside one data node. Fine, guys, so we'll move forward and focus on the last new feature of Hadoop 3. So it is nothing but task heap management. The Hadoop heap size variable has been deprecated, and in its place, Hadoop heap size max and Hadoop heap size min have been introduced. Default heap sizes have been removed. This will allow the JVM to use auto-tuning based upon the memory size of the host to re-enable the old default configure. All global and daemon-specific heap size variables now support units. If the variable is only a number, the size is assumed to be in megabytes. Fine guys, so these are all the new features that are there in Hadoop 3 when we compare it with Hadoop 2. So as I told you earlier as well, it is still there in alpha phase, so it has to first go to beta phase and then it will go to the production phase. And after that, we'll be coming up with new videos about Hadoop 3. We'll see how to perform hands-on using Hadoop 3. So thank you for watching this video. You can comment your queries and questions. Do subscribe to our Edureka channel to learn more. Thank you and happy learning.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!